We know that qualitative behavior of linear systems can be easily described by looking at the eigenvalues of the system matrix. For nonlinear systems, qualitative behavior, as we learned, it can be described by using phase portraits. However, you know that this approach of phase portraits, that is limited to second order nonlinear systems. And furthermore, you have also learned that sketching phase portraits, that is somehow difficult. So is there any other way to describe the qualitative behavior of nonlinear systems? So yes, the near equilibrium point behavior can be described by linearizing the system at the equilibrium point. So in today's lecture, we shall talk about this approach, that is linearization approach to study the qualitative behavior of nonlinear systems near equilibrium points. For that purpose, let's again consider a second order nonlinear system described by these state equations f1 and f2. These are two nonlinear functions of the state variables x1 and x2. Let P be an equilibrium point for this system. P is a vector with the P1 and P2 as its elements, and you already know how to determine the equilibrium points. Substitute all the derivatives equal to 0 and solve the equations for x1 and x2. That gives you the equilibrium points. We can obtain the Taylor series expansion of this nonlinear function. You already remember the procedure. The Taylor series is this f1 evaluated at this equilibrium point, and then partial derivative of this nonlinear function with respect to x1, and this thing evaluated at the equilibrium point multiplied by x1 minus p1 plus the partial derivative of f1 with respect to x2, this thing evaluated at the equilibrium point multiplied by x2 minus p2, and some higher order terms, quadratic term and terms with higher orders. Similarly, this second equation, we can also find Taylor series expansion for this second equation. So x2 dot is this function evaluated at the equilibrium point, and then the partial derivative of f2 with respect to x1, this evaluated at the equilibrium point multiplied by x1 minus p1, and likewise here is a typo, it is partial f2 over partial x2. This is not f22, it is f2. Its partial derivative with respect to x2, and this thing evaluated at the equilibrium point multiplied by this thing and higher order terms. So you are already familiar with the Taylor series expansion of nonlinear functions. Since this is equilibrium point, and how did we define equilibrium point? At equilibrium point, all the derivatives are equal to 0. That is, f1 evaluated at this equilibrium point, that is equal to 0. Likewise, f2 evaluated at the equilibrium point, that is equal to 0. It means that in this expression, this thing is equal to 0. Likewise, this thing is also equal to 0. Furthermore, this derivative, this partial derivative of f1 with respect to x1, this will be another nonlinear function of x1 and x2. However, when x1 and x2 are substituted by these constant values, that is the equilibrium point, this thing will be a constant, right? So let's call it, give it some name, a11. Likewise, this will be a constant, this will be a constant, this thing will be a constant. We can give some names to these constants, a12, a21, a22. Therefore, this first equation, that is simply equal to a11, that is this term, multiplied by x1 minus p1, and likewise this term a12 multiplied by x2 minus p2 written over here, plus some higher order terms. Similarly, the second state equation can be written in terms of a21 and a22. So this equation is the same as this equation with a11, a12, a21, a22 as defined on the previous slide. We are interested in the near equilibrium point behavior of this nonlinear system. So let's define new state variables z1 equal to x1 minus p1 and z2 equal to x2 minus p2. With this definition, what will be z1 dot? Z1 dot will be equal to x1 dot. P is some constant, its derivative will be 0. So z1 dot is equal to x1 dot, and x1 dot is written over here. That is z1 dot is simply equal to a11, and this is z1 plus a12, and this is z2 plus higher order terms. Likewise, z2 dot is simply equal to x2 dot, and x2 dot is given by this expression, which is written over here in terms of z1 and z2. So these state equations and these state equations are the same, written in another format. Over here, what are higher order terms? What are these terms? These are some terms with powers of this difference term and powers of this difference term. Likewise, powers of this difference term and this term. These are denoted by higher order terms. So near the equilibrium point, that is when x1 is very close to the equilibrium point p1, and likewise x2 is very close to p2, then this thing will be a small this thing will be small, its square will be further small, and its third power and higher powers will become more and more smaller. Therefore these higher order terms are smaller near the equilibrium point. So near the equilibrium point, these terms, higher order terms, can be ignored, and in that case these state equations are approximately equal to these state equations. So remember that here we have approximation. Up to this point there was no approximation. These state equations were exactly equal to these state equations written in another format. However, here these state equations are not exactly equal to these state equations because we have made some approximations. We have omitted the higher order terms, and we can ignore these higher order terms as long as these differences are small. That is, as long as we are operating near the equilibrium point. So near the equilibrium point, this nonlinear system can be approximated by a linear system. And for linear systems, here this A is given by this matrix with A11, A12, A21, A22 as its entries. You already know how to write these state equations into this form. If you write it in this form, A is equal to this matrix, where a11 is the partial derivative of f1 with respect to x1, and so on, all the things evaluated at the equilibrium point. Uh, a short notation for this one is partial derivative of f with respect to x. Here f is a vector and x is a vector, so partial derivative of a vector with respect to a vector will be a matrix given by this expression, and this thing evaluated at the equilibrium point, that is some constant matrix A. This matrix is called Jacobian matrix, and this thing, that is the Jacobian matrix evaluated at the equilibrium point. And this kind of linearization, that is called Jacobian linearization. For linear systems, you already remember that qualitative behavior can be described by the eigenvalues of the system matrix, and the near equilibrium point behavior of this nonlinear system can be described from the behavior of this linear system. However, that behavior will be applicable near the equilibrium point. So that statement is written over here. Trajectories of nonlinear system in a small neighborhood of equilibrium point are close to the trajectories of its linearization about that point. So whatever are the trajectories of this system near the equilibrium point, the trajectories of this system near that equilibrium point will be approximately the same. For linear systems, you already know equilibrium point for linear systems, that is that can be a stable or unstable node, that can be a stable or unstable focus. It can also be a stable it can also be a saddle point. And in the small neighborhood of the equilibrium point, the trajectories of nonlinear system will behave like stable node if its corresponding linear system is a stable node, or unstable node if this is unstable node. And this nonlinear system near the equilibrium point, it will behave like a stable focus if its corresponding linearized model behaves like a stable focus, and likewise for unstable focus it will behave as unstable focus. If a linearized system behaves like a saddle near the equilibrium point, this nonlinear system will also behave like a saddle near the equilibrium point. There is one exception. The exception is over here. If the eigenvalues of this matrix, these are purely imaginary, what will be the behavior of this linear system? Oscillations. And what do you expect, what will be the behavior of this nonlinear system near the equilibrium point? So we cannot say anything. We cannot say anything. So if the eigenvalues of A are on the imaginary axis, the qualitative behavior of the nonlinear system near the equilibrium point, that cannot be predicted by just looking at the eigenvalues of this matrix. Right half plane are stated over here. If we have unstable node, unstable focus, and saddle point, so these correspond to the right half eigenvalues on the right half plane. जी बिल्कुल. If the eigenvalues of this matrix are on the imaginary axis, only then we cannot predict the qualitative behavior of this nonlinear system by looking at the eigenvalues of this linearized model for that particular system. Is it clear? This model we have already studied, tunnel diode circuit. Here we have tunnel diode. For tunnel diode, voltage and current, these are related by this nonlinear relation, where x1 is the voltage across this diode, and this h of x1, that is current flowing through this diode. And the equations which describe this electrical circuit, these are given by these state equations. And the equilibrium points, there are 3 equilibrium points for this system, one at this location, the second at this one, and third at this one. So one strategy, as we studied earlier, is to sketch the phase portraits for this system to study the qualitative behavior. However, you remember sketching phase portraits is not an easy task, that is quite difficult. So we shall linearize this system at the equilibrium point, And by looking at the qualitative behavior of the linearized system, we shall predict the near equilibrium point behavior of this nonlinear system. So for that purpose, we find the Jacobian matrix. Jacobian matrix is given by this relation: partial derivative of f1 with respect to x1. What is its partial derivative? Partial derivative of f1 of this term with respect to x1, that is 0. So partial derivative of this h with respect to x1, that is written over here with a negative sign, and 0.5 is from here. And then partial derivative of f1 with respect to x2. So partial derivative, this h of x1, its partial derivative with respect to x2, that is 0, because this is only function of x1 written over here. So partial derivative of this term with respect to x2, that is 1. 1 multiplied by 0.5 is written over here. Partial derivative of f2 with respect to x1. So partial derivative of this with respect to x1, that is minus 1, and minus 1 multiplied by 0.2, that is written over here. Partial derivative of f2 with respect to x2, so that is minus 1.5, and minus 1.5 multiplied by 0.2, that is 0.3. What is this thing? Partial h over partial x1. So partial derivative of this h with respect to x1, that can be evaluated from here, is this is 17.7 minus 2x1 multiplied by this thing, so that is written over here. Partial derivative of h with respect to x1, you can easily evaluate this partial derivative. So how did we define this A? A is the Jacobian matrix evaluated at the equilibrium point. Let's evaluate it at first equilibrium point Q1. So simply substitute x1 equal to this thing and x2 equal to this thing into this matrix. You get this matrix, and this is the Jacobian matrix evaluated at this first equilibrium point. So you can easily find the eigenvalues of this matrix. So eigenvalues of this matrix are given by these are equal to minus 3.57, and the second eigenvalue is minus 0.33. So what is the qualitative behavior of this system near this equilibrium point? Eigenvalues are both negative and negative and real, so that is stable node. So qualitative behavior of this nonlinear system near this equilibrium point will also be a stable node. Again, we can evaluate the this Jacobian matrix at the second equilibrium point. This matrix is comes out to be equal to this one, and find the eigenvalues. Eigenvalues of A2 are given by 1.77 and minus 0.25. So what will be the qualitative behavior of this nonlinear system near this equilibrium point? Saddle. So qualitative behavior of this nonlinear system near this equilibrium point will be saddle. Third equilibrium point, we evaluate this Jacobian matrix at the third equilibrium point. We have this matrix. Eigenvalues of this matrix can be easily computed. These come out to be equal to minus 1.33 and minus 0.4. So what is qualitative behavior? Stable node. So qualitative behavior of this nonlinear system near this equilibrium point will be stable node, and that is what we have seen from the phase portraits already. A few more examples. This is example of a pendulum system. Equations of pendulum are described by these state equations. This system has multiple equilibrium points given over here, and we want to study the qualitative behavior of this system using linearization technique. Jacobian matrix is given over here. You can easily find this matrix. You can compute these partial derivatives. These come out to be, this matrix is given by this expression. Let's evaluate it at different equilibrium points. This matrix, Jacobian matrix, evaluated at this equilibrium point, that is 0, 0. We have this system matrix. The eigenvalues of this system matrix, these can be easily computed. These come out to be complex with the real part, negative real part. So what is the qualitative behavior of this nonlinear system near this equilibrium point? It is a stable focus. That is, it will show oscillatory response, decaying oscillations. Near the second equilibrium point, we have this matrix, uh, and these are the eigenvalues. So what is qualitative behavior of this nonlinear system, near this equilibrium point? That is saddle. And now you know the meaning of all saddle and focus, you know the meanings. That is what we have already seen from the phase portraits. This equilibrium point was a stable focus, and this equilibrium point was a saddle. So near equilibrium point can be near equilibrium point behavior of nonlinear systems can be described by using the this Jacobian linearization. There is one exception. If the eigenvalues of this matrix are on the imaginary axis, then the qualitative behavior of nonlinear system near the equilibrium point, that cannot be predicted. Example is over here. We have a nonlinear system given by these state equations where mu is some constant and x1 and x2 are states of the system. Jacobian equilibrium points, one equilibrium point of the system is at this location. Jacobian matrix, the partial derivative of f1 with respect to x1 can be easily computed. The partial derivative of this term with respect to x1 is 0. Partial derivative of this expression with respect to x1 is computed and written over here, and likewise the other partial derivatives are also computed. Let's evaluate it at the equilibrium point, and this Jacobian matrix evaluated at this equilibrium point by substituting x1 equal to 0 and x2 equal to 0. This term is 0. What is here? Minus 1. This term is 0, and here is plus 1, and this term is 0. This is 0. So we have this Jacobian matrix evaluated at the equilibrium point. Eigenvalues of this matrix, these are purely imaginary, and hence we are not able to describe the qualitative behavior of this nonlinear system near the equilibrium point utilizing the Jacobian linearization approach. So here are the phase portraits for this system for some positive values of mu, and here is the phase portrait for mu less than 0. So phase portraits, we can see that it is stable focus for the case of mu greater than 0 and unstable focus for mu less than 0. However, we were not able to describe that behavior by looking at the Jacobian matrix. In summary, this Jacobian linearization technique can be utilized to predict the near equilibrium point behavior of nonlinear systems. There is one exception over there. This linearization approach fails, and that exception is over here. And remember that the point to emphasize is that this approach can only tell about the near equilibrium point behavior of the system.